Anyway, yeah, hello. This is part 3. We are going to describe the basic functionality of the payload we have been designing for the past 2 videos, and I'll just go through what I have come up with in this video. So we designed the power supply in the previous part 1 of this payload design structure design, and you can see that we have 5 volts getting into regulator that is giving out 3.3 volts. We have a couple of decoupling capacitors at this point here, and then from there we have the camera module, which is the star of the show. Basically, this camera module is going to be connected through DCMI interface to the MCU, right? So I can just add it here. So these pins are connected to the DCMI interface on the STM32, which means, if you remember us configuring it, these are the pins that are going to be used: 8-bit parallel data input, and a few of synchronization and setup config pins. So that's that. Then we have another part here, which is a payload detect. Basically, it's going to tell the OBC that the payload is inserted on the stack of the cube, right, or CubeSat, right? So we can start routines or functions that have to deal with the CubeSat payload. Right here I've included the NTC thermistor, basically to measure the board temperature. So this is going to measure the temperature of the payload, and it's going to transmit this to the OBC board, and it's also going to transmit this temperature to the onboard MCU. I have placed just a placeholder here for serial wire debug, but it's not going to be used because remember we said that we are going to program this board from the OBC, right? So that we reduce the component count, although it's just one, but I want to test and see whether we can use the OBC as the motherboard for this payload. Next, we have a simple user LED here that can be used to run or blink at different routines, maybe PWM, maybe whatnot, just to indicate some activity on the payload. Next, we have a UART debug here. So this UART debug is to be used to test, or rather to transmit data from basically the onboard, the onboard MCU, yes, to a USB channel, a UART channel, right? So it's very critical during testing that you have means of peeping into what's going on in the MCU right here. Next we have, I talked about the clock, 16 megahertz connected to the MCU. Then we have just some supporting functionality for the STM32 MCU, like the boot option. You can select between 3v3 and ground. Just to clarify that, it's right here. So this is what is normally used, so let's place it right there. So boot toggle, basically you place boot 0 at 3v3, it is in download mode, and it can accept programs through the serial wire debug programming port. If you place it in ground or to ground, connected to ground, it will go into run mode, so it will fetch what program has been downloaded and then start executing it. This is our basic reset pin, just to restart the program. Basically, this is pretty typical. 10K pulled high, debouncing RC here, then connected to the and reset pin of the MCU. Then we have now the MCU that has the ability to have DCMI interface. So you realize that on the OBC I'm using STM32F401CC U6. This one does not have digital camera interface, or the DCMI, right? So you can still use a camera with this, but you would need additional circuitry. For example, the clock speed of this is too low and does not have a dedicated buffer for the camera data. So what you do, you include a buffer here, separate, right, FIFO, first in first out buffer for the camera, and then you connect the camera to that buffer, and from the buffer to the MCU. So that's an additional hardware is needed here. That would be possible, yes, but you need to reduce, of course, the cost of the board. So what I chose to do is to just use an MCU, decouple this, use an MCU that has a DCMI, right? And this was the cheapest and the best I could find for the the resource I have. So this is going to be perfect for such use. Next is SDA SCL. This is I2C connection. We have what else do we have? Right, that's all we have for this board. Next, I'm going to explain this connector here. So this is a IDC connector, right? 16 pins. So remember, from our structure, if I may open it real quick, let me see where I have it. Right here, projects, that payload, let's see, images, payload structure. Yeah, so this is the structure we are designing, or rather we are following, right? So you see, this is a JST connector header that will be going to the motherboard. The motherboard is the OBC, right? So the OBC needs to receive all the data from this payload module, and that data can be transmitted in different ways. So I have put ability to use SPI, right? You can see these 4 pins here for SPI. Then you can use SDA or SDA and SCL, which is I2C basically, plus other signals that are needed. 5 volts ground. So this is 5 volts is going to supply this one here. I just realized I named it differently, so it will be like that. 5 volts ground. You need payload detect. LDO enable is a way of switching on and off this regulator. So basically you can activate and deactivate the payload as you wish, right? Mostly that is useful when you are in orbit, when you're in a place where you don't need to take the pictures. If these are not, again, another observation, CubeSat. So if there's a area above Earth you need to take pictures, you don't need to take pictures on the other sides or the other areas. Plus, when this payload is on, it is consuming power, right, when it's active. So you can turn it off to save battery power, right? Yeah, so that's why I included that LDO enable and disable. And payload temperature, basically you should monitor the board temperature of this camera module. It's a CMOS sensor, so basically it can be destroyed very fast, very easily by high temperatures. Zero wire clock, zero wire data in out is for programming this. So this part is connected to this, right, and this other one, DIO. Right, so I just want, in this video I'll just like cross check if I have everything that I need before we do the layout. Probably in the next one it's going to be short and to the point. So I have the DCMI is set up correctly. Payload detect is connected to this, should not be connected to this MCU. Payload temperature, I don't think I have payload temperature here, but it's not there. So right there we should use an analog, an ADC channel. So as usual, we go to the CubeMX configuration tool, we look for ADC, right, the one that does not have conflict. We just want high reliability at this point. Then enable it, it gets set right here. So I'm gonna rename it to payload NTC, or yeah, payload NTC, right? then in EasyDA I can rename this again to match. It's just easier when they are matching names between the schematic and the what configuration tool. So that's PS0. Copy this net label, bring it to PS0. PS0 is, where is it? It's right here, right there. So I can remove this and reroute it that way, then put this one there, PS0. Good. Okay, save. So this is check. Payload NTC. I need to re-update this pin here, so NTC like that. Next is user LEDs. I think it's there. Okay, that's okay. OSC in, OSC out, that's okay. And reset, that's good. Boot option is good. Boot 0, boot 0, boot 0 should be somewhere here. Yeah, boot 0 is right there. And then DSMI again is fine. I squared C. SDACL. SDACL is, where is it? It's right here. I've pulled these two high, but they are being connected to the OBC, which means the OBC might be pulling them high too. Let me check that. We don't want to pull it high twice, so I don't know whether it's pulling it. I don't remember that. Let me check. This is the OBC schematic. So are they pulled high? Where's SDS here? It's right here. SDA and SCL. Let me think. Who is responsible for pulling it high or low? I mean, for pulling the channels high. So if this I2C is coming from, for example, the comms board, let's see the comms, whether it's pulling the I2C high or not. It's not also. So I'm just scanning for two resistors that are connected next to each other to 3v3, but there is none, there is none, there is none. Okay, so let's add that functionality on the OBC. So OBC is here. Right, so what I'll do, I'll copy this schematic here, save it first, then copy these two resistors, bring them to the OBC right about there. Yep, so right here you can say this is SDA and this is SCL. You can do that, you can do that. Okay, so they are pulled high. Right, that's fine. So SDA is okay. We can remove these two. We don't need them anymore. Delete that, delete and delete. Okay, so next is we check SPI, right? Mosi Miso SCK. I don't think it's there. Mosi Miso SCK. It's not there. So next we go to the configuration tool. We look for SPI under connectivity, SPI1. Let's see whether you can enable full duplex master. No, it's not a master, right? It's a slave. So it's going to be sending data to the OBC. So I'll set it as a slave. And I check for those pins, SPI pins. SPI SCK is SCK SPA5. SCK SPA5. So just route it that way and give it the name that is right there. That's the net label for the same SCK. Next is SPI Mosi SPA7. So Mosi is right here, PA7, this is Mosi. Okay, miso, let's check. Where's miso? SPI miso is PB4. Let's look for that. PB1 2 0 1 2. Where is 4? 4 is right here. PB4. Okay, PB4 is a what? Miso, yeah. This is miso. PB4 miso. Next, what is remaining? CS. So I don't think it has given us a CS pin. We can control that with hardware. Yeah, it's not there. I can choose whichever pin I want it to be SPI SCK, right? So you see, for example, here we can enable the hardware NSS, which is slave select active low for N, right? If we enable it, they should set it somewhere. SPI 1 slave select is PA15, which is, it still works fine, or we can use our own pin if we want. So this pin is going to be called CS, right? I think I'll rename these net labels to match payload CS etc, but they are still fine because they are hierarchical, so they are confined within the sheet. There will be no conflict of names for this case, right? So we have resolved the the SPI. I think everything here is fine. I think everything is, the schematics functionality is fine, right? So I can save this, but if we get any like missing thing, we can add it. I'll save this to generate the code. Remembered my decision, yes, generate, and yes, so they'll generate those configurations and we can start our programming here. But this is, I'm not going to do this in this video. Basically everything is set and yeah, we're good, right? So if I save this, one thing I wanted to show you is that if I save these guys, these are 3 schematics, and go to PCB, export or rather update to PCB, what you will realize is that component lacks property footprint. Which one? Yeah, the camera does not have a footprint. I've not created the footprint for this yet. Anyway, so what I wanted to show you is that you realize that all these schematics are on the same PCB, right? For a reason. The reason is I will panelize these schematics, all of them, right? Not really panelize, but put them on the same PCB and then use like slots to separate. So what I'm saying is, for example, if I have this layout, I can copy that and I think I can paste it here, just next, I can paste it next to this one, right? And then separate them. So I'll have the OBC, the comms, the payload. The advantage is that it reduces the cost of production, so you don't have to pay for separate PCBs and engineering fee. You can easily do this, but of course I'll check first to see which one is more cost effective. Yep, so let me not do that, save, and yeah, so the camera or the payload is right. Payload should select those. Anyway, I'll not select them. Did it even add them? Let me see. Design update. Found some pins connect floating, which is okay. basically you're not supposed to produce any PCB with any warnings unless they are really like insignificant, but yeah, unless this is a fatal error. So I think it does not produce the PCB because of that. So what I can do is exclude it from being inserted into the PCB for now, before I create the footprint. Right, save, and then go to design, update. It should show me the updated components. Yeah, so apply changes. Okay, cool. So yeah, this is the connector I was looking for. It's right angled. Let me see if I can render this in 3D and see if we have just a visual of this dirty stuff. Yeah, here are all the components, right? They are not laid out, so I don't know whether that connector is here. It looks weird, but yeah, anyway, yeah, this is the OBC. I think, is it the OBC? I think this is the OBC with the SD card, etc. Yeah, right. So that's it for this video, and next time we'll create the footprint for the camera and, you know, start basic layout for the PCBs, and we'll see how that goes. Otherwise, all the best, and see you next time.